Okay, so today we will start a new chapter, chapter 9, the inference for regressions. And today's lecture is just the inference for a simple linear regression. So simple linear regression means we only have one explanatory variable. Okay, so there is a y response and x is the explanatory variable. So before we start, there is one thing you may want to know. So this is the formulas for I think everything in chapter 6. This handout called CH6 handout. It is already uploaded to Canvas. You can check it. I think this is a pretty nice summary of what we have learned in the one sample and the two sample inferences. Okay. Okay, so before we talk about the inference for the simple linear regression, let's first do a quick review of the simple linear regression. We have talked it in chapter 4, and this is one example we used. So this is a ceramic example. There is a certain kind of ceramic compound, and we use different pressing pressures to make some specimen, and we measured the densities. This table is the data table in this problem. So the x is the pressure, the explanatory variable, and the response y is the density. And there are 5 levels of x used in this experiment. And for each level of x, we have 3 replications. And if you make a scatter plot of x and y, you'll get something like this. So there are 3 dots for each x. And you can see that the relationship is approximately linear around this scatter plot. And so you can just draw a line to connect these points, and in a way such that these points are very close to this line. And this is the line we obtained. And the line, we call it the regression line. Once you have got a regression line, you can do a lot of things. So once you have fit a regression line, you can use it to predict future values for y based on x. So for example, you want to predict a density under x equals 5,000. And you can use the regression line by plugging x equals 5,000 into that regression line, and you get 2.618. This is just the prediction of the y value based on x. And The line is also used to characterize the relationship between x and y in terms of strength, direction, and shape. Okay, so in the ceramic data, because you have seen that uh, the points are very close to this regression line, and you know that the relationship between density and x is the pressure, is a strong positive linear relationship. Okay, it is positive because y increases as x increases. And we can also say that on average, the density increases by this much. This is the slope of the regression line. The density will increase this much for every increase in pressure of 1. Okay, so with the regression line, you can do such a conclusion about the relationship between x and y. But all this should be restricted in the range of data. Okay, so in this example, the x is from 2000 to 10,000, so the range should be restricted to x from 2000 to 10,000. So how do we fit this linear regression line? What we did is that we used the principle of least squares. We first assumed such a linear form to describe the relationship between y and x. And then we find the optimal b0 and b1 by minimizing this loss function. This loss function is the sum of squares of yi minus y hat, where y hat is the b0 plus b1 xi. Okay, and by minimizing this loss function, which is minimizing these squared. So this is a sum of this is just the sum of squared distances of the observed yi to the fitted line. Okay, this plot shows y. So we want to make the points as close as to the fitted line. And we have shown the derivation of this normal equations. So what we did is that we used the partial derivatives to get these normal equations. And by solving these normal equations, you get the formulas for the least square solution for B1 and B0. Okay, this is also an example we have seen before. So this is a plastic hardness data example. We made several batches of plastic, and we allow some time for those plastic to harden, and our explanatory variable is x time, and the hardness of the plastic is the response y. And the measure of hardness is assuming that when time is 0, so for the freshly melted plastic, the hardness is 0. But in our data, we start recording the response when time is 32. The range is from 32 to 56. And in this range, when you make the scatter plot, you can find that it's also like a linear relationship between time and hardness. So we can use the regression line, a linear relationship, to fit this data. So this is just to plugging the data into the formula. We calculated, this is the denominator, this is the numerator. And we get the B1, and B0 is y bar minus B1 x bar. And then you can plot the regression line on top of the scatter plot. This is what you get. And from the plot, you can see that the points are pretty close to the regression line. So that means the fit is not bad. And that also means the relationship between time and hardness in this range. In this range is pretty strong because the linear fit is very good, and it is also positive. Of course, it's a linear relationship. So you can say that there is a strong positive and linear association between time and hardness of the plastic. And to interpret the fitted B1 and B0, here's what you can do. So B1 equals 2.43 means that on average, the plastic hardness increases 2.43 more units for every additional hour. Okay, and B0 equals 153.19 means that if the model is completely true at the very beginning of the hardening process, which is time is equal to 0, the plastic hardness should be this number. So this is one thing you need to be careful, because for this data set we have known that the plastic were completely molten at the very beginning, so at time 0, and the hardness should be 0. That means this interpretation of B0 is not true. So this assumption, the model is completely true, does not hold. Okay. So this is because we are extrapolating. We don't have the data that is close to time 0. Maybe at that time, the relationship between the time and the pressure is not linear. And when you still assume a linear relationship for the range that we don't have any observations, then there is some problem. So don't extrapolate. So extrapolation means that you predict y values beyond the range of the x data. Okay. In this case, if you predict y at x equals 0, you are making such a mistake. And we've also talked about to measure the usefulness of the linear regression. So the usefulness means that the goodness of fit means how good a linear fit is for this data. Okay, and by saying that, we have assumed that the true model, the true relationship is linear. Okay, so the linear model is a valid model here. Then we talk about the usefulness of the linear fit, or how good a linear fit is to this data. And the first thing we use is a linear correlation. It is a measure of the usefulness of a fitted line, and it is defined by this formula. And there is a shortcut. You can use B1 and Sx, the standard deviation, the sample standard deviation of x, and Sy, the sample standard deviation of y, to just get the R. So this linear relationship measures how strong the linear relationship is between x and y. And so in this page, we can do a quick review about this statement. And first, the linear correlation is always between -1 and 1. And when the linear correlation R is less than 0, that means we have a negative slope in the linear regression, and the relationship between x and y is negative association. And when R is greater than 0, that means we have a positive slope, and there is a positive association between x and y. And as R, the absolute value of R, is getting closer to 1, that means that x and y are having a very strong linear relationship, or a high correlation. And if you have a low value of absolute value R, which means that the R is getting closer to 0, that implies a weak linear relationship or low correlation. And on the first row of this figure, we can see that how different magnitudes of R can get us different strengths of a relationship. So on the two ends, so on this end, when the linear correlation between x and y is 1, then it is a perfect linear relationship, and it is positive. And when R is -1, it is a perfect linear relationship too, but the direction is the opposite way. So there is a negative association between x and y. And when the magnitude is 0.8, so the linear relationship is weaker, so you can see more variabilities, but you can still find that there is a linear pattern between x and y. And when the magnitude gets to 0.4, you can see that the relationship is getting weaker. So there is more variabilities. And when the correlation is 0, then you can see that it's almost a circle cloud, and there is no really relationship between x and y. You cannot see any directions or any associations between x and y in this scatter plot. And the second row shows you that as long as the relationship is completely linear, you always get 1 or -1 for the linear correlation. And for these three, you got a positive association between x and y, so the correlations are all 1, although the directions of these three lines are different. And when you have negative associations, you got -1, although the directions are not the same, but the linear correlations are all -1. And the other measure we used is the coefficient of determination to measure the usefulness of fitting line. So this measure is actually the variabilities explained by a linear model, or you can say that the information explained by the linear model provided the data. And this is a formula for R squared. And the interpretation of R squared is the fraction of variation in the response variable y explained by the fitted line. So because you can also say explained by the model, because the model here is just a linear regression. So you can use the fitted line instead of model here. And we also know that the relationship between R squared and the linear correlation, little r, is this. So R squared is equal to the square of the little r. And for the theoremic data, we have that the R squared is equal to this number, 0.98. So that means that 98% of the variation in the density, this is the response y, is explained by the pressure. Or to be more exact, is explained by the linear model with pressure as explanatory variable. So hence, because a lot of variation in the data is explained by the model, which is the linear model. So we can say the line is useful for predicting the density from the pressure. And for the plastic data, the R squared is also very high. It is about 96%. So 90, so around 96% of the variation in the hardness. So this is also why is explained by the linear model with time as explanatory variable. And we can say here that a line is useful for predicting hardness using the time, because the variation explained is very high, and that means so you can think of the variation as some kind of information. So you can think of that the information contained in the data are captured by the linear model very well. Okay. So that is the quick review of the simple linear regression, SLR. And now let's formalizing the simple linear regression model for the inference. So until now, we have this form of the simple linear regression. Yi, the response, is equal to B naught plus B1 times Xi times a residual, plus a residual. Okay. And Y1 to Yn are observed values of the response variable, and X1 to Xn are observed values of the predictor variable or explanatory variable. And B naught is estimated slope using the sample. And B1 is also the estimated intercept based on the sample. And EI is a residual of the ith unit of the sample. So you can see that we do everything on the sample. So recall what we want to do using the statistical inference. We want to infer something about the population using the sample. So we will be using this estimation to infer the knowledge in the population. So to do that, we need to make some assumptions about the population. So this is the true model. We are assuming that i's are the response variables, and we have some xi's, which are the predictor variables. And the B0 and the B1 are parameters. So they are true. They are the true intercept and the true slope in the population. And we have also an error term, epsilon I. Epsilon 1, epsilon n are random variables, and they are called error terms. So here in this model, you can see that we have this error terms. It is random variable, and this is not random variable. Xi is constant, and yi, because epsilon I is a random variable, so yi is also a random variable. And the assumption we made on this random variable, the error terms, epsilon 1 to epsilon n, is that they are IID normal with a variance sigma squared. So that means they are not, so yi's are independent, they're not IID. So yi's are independent with mean beta naught plus beta 1 xi, and the variance is also sigma squared. Why? Because we know yi is equal to b naught plus b1 xi plus epsilon I, right? So epsilon I is a normal random variable, so yi should also be a normal random variable, and this is just a constant. Okay, right? So we know that ei is just beta naught plus beta 1 xi plus e of epsilon I, and this is 0, so we have beta 1 naught plus beta 1 xi. And the variance of yi is just variance of epsilon I, because this part is a constant, and it is sigma squared. Okay. So sometimes, and you can use this notation to denote b naught plus b1x. We use mu of y given x to denote this mean. Okay. So actually, if you do this, each yi are independent, normally distributed with mean y given xi, and the variance is sigma squared. So this plot shows you the meaning of this model. So in this model, we are assuming some true, a true line, beta naught plus beta 1x. And for each x, for example, this x, for each x, the y has a bell-shaped distribution, a normal distribution around this center. So this corresponding point on the line is the center of the distribution of y. And the y could be anywhere here, but there's more possibility around this center because you've got a high peak around the center for the normal distribution. And so now we already have a formal model for the simple linear regression. The next thing we need to do is to estimate the parameters. And there are 3 parameters here, and we'll first talk about estimating the sigma squared. What we used to estimate the sigma squared is use something called the line fitting sample variance. Recall that we use y hat to denote b naught plus b1 xi. This is just the sample estimation of the intercept and the slope, and the residues are EI, which is yi minus yi hat. So what we call a line fitting sample variance is this. This is the sum of squares of the residues, and the whole thing divided by n minus 2n is the sample size, is what we call a line fitting sample variance. And this is a fact about the line fitting sample variance. The expected value of SLF squared is sigma squared. So this means that this estimator, this is an estimator of the sigma squared. This estimator is an unbiased estimator of sigma squared, because the expected value of SLF squared is just sigma squared. There is no bias. And of course, the line fitting sample variance, the sample standard deviation is just the square root of the SLF squared. Okay, so let's look at this Hermix example again. We again have the pressure as our predictor variable and y as our explanatory, y as our response variable, and 3 replications for each level fx, altogether 5 levels. And this is the least squares line we have. So to estimate the sigma squared in the formal linear model, we will first calculate the y hats, the fitted response variable, and we calculate this sum of squared residues, and we have this number. Then SLF squared is just the sum divided by n minus 2. N is 15 here because we have 15 observations, and we got 0.00396. And the sample, the line fitting sample standard deviation is just the square root of that, which is 0.0199. And the next thing we want to do is that we can use those residuals to check the assumptions. And here we introduced another kind of residual called a studentized residuals. The motivation for introducing the studentized residuals is this. In the model assumption, we assume that epsilon1 to epsilon n are highly normal with mean 0 and variance sigma squared. And this is the fact. EIs. Now EIs are also random variables, and the expected value of EIs are all 0. But the variance of EIs are not all the same. The reason is that we are estimating the slope and the intercept instead of using the true slope and intercept. So that means that epsilon I is yi minus beta naught minus beta 1 xi, and epsilon I is the expectation of epsilon I is 0, and the variance is of epsilon I as sigma squared. But EIs are yi minus beta naught minus beta 1 xi. Because we are using EIs are y minus b naught minus b1 xi, because the b naught and b1s are all estimated, so they are also random variables. And because of this, the variance of EIs are not sigma squares anymore, unless the b naught and b1s are exactly the same as beta naught and beta 1. So what we got is this. So the variance of EIs are actually like this. So this is the variance of the J's residue. It is a sigma squared times this thing. So this would be a different number depending on the xj you used. So because of this fact, the variance of each residues are not the same. So we want to normalize it to make it the same. So that's how we define the studentized residue or standardized residue. Sometimes you can call it studentized residue. This is another name for this. It is EJ star. EJ star is EJ divided by this whole thing is just the standard error of EJ, right? If you do the square root of this thing, you will get sigma times the whole thing inside. But since the sigma is unknown, we use the SLF to replace the sigma. So this is just in the denominator it's just the standard error of EJ. And under the model assumption, the EJ stars, the standardized residues, should be approximately normal 0, 1. So in the ceramic state example, for each x, we first calculate the denominator for the standardized residues for each x. And then we do EJ divided by this thing. And we got the standardized residues. This is the normal quanti-quanti plot using the raw residues. And this is the normal quanti-quanti plot using the standardized residues. And you can see that for both of them, it's like it's like that the points are falling around a straight line. So that means the model assumptions is plausible because you, from the normal quantum plot, you find that the residues are almost normal. And although you can still find that the such kind of normal assumptions using the raw residues, but rigorously, it is better to use the standardized residues because based on your model assumptions, theoretically, the residues, the raw residues are normally distributed with different means. So just checking the raw residues may not be enough to verify the model assumptions. So that's why you'd better use this standardized residue to check the model assumption where we assume that the epsilon 1 and epsilon n are normally distributed. Okay, the next thing we will do is that we will do some inference for the slope parameter. So there are three parameters in this simple linear regression model, and the one that we are so B1 is of special interest because this is the parameter that described how the linear relationship is in this model. And we want to make inference about this parameter. And B1 is estimated from the data. So it is also a random variable. And it is actually an estimator of the true slope beta 1. And under the assumptions of the linear regression models, we have this. B1 would be a normal random variable with mean beta 1, and this sigma squared divided by the sum of xi minus x bar squared is the variance of B1. And from here, you can also see that because the expected value of B1 is beta 1, it is also an unbiased estimator of beta 1. So due to this fact, you have this Z equals to B1 minus beta 1 divided by the standard deviation of B1 is a normal random variable, standard normal random variable. But since the sigma is unknown, we use the estimator SLF to replace the sigma. And when you replace sigma with SLF, then this thing is no longer a standard normal random variable. It would be a T random variable with degrees of freedom n minus 2. And this is also the test statistic we'll be using for the inverse. So if you want to test that, if you want to do a test when the null hypothesis is beta 1 is equal to some number, this is the test statistic you will be using. You just replace this beta 1 here with the number in the null hypothesis. And this test statistic has a t n minus 2 distribution if h naught is true. And also the assumptions for the simple linear regressions should also be true. And for the two-sided confidence interval, you have this. This is B1. We have a 1 minus alpha over 2 quantile for the t and minus 2 distribution. And here we have the standard error of B1. And for the one-sided confidence intervals, it's similar. So if, for example, for the lower one-sided confidence interval, you would use t and minus 2, and then the quantile should be 1 minus alpha quantile, because it's a one-sided confidence interval. And you will also use B1. And the right hand would be infinity. Okay, so let's again use the ceramic data as an example for the inference for the slope. What we will do is that we will construct two-sided 95% confidence interval for beta 1, okay, which is slope. First, we get the estimator of beta 1, which is just B1. It is 0.000487. And we get the denominator and SLF. So these two are for the standard error of B1. Then we also calculated the quantile needed for the confidence interval. It is T13 and the 0.975 quantile, because we are constructing two-sided 95% confidence interval. So alpha is 0.05, 1 minus alpha over 2 is 0.975, and n minus 2, n is 15. We have 15 observations, and minus 2 is 13. So you can look up this number in table B4 in the textbook, and you got a number of 2.16. So the next thing is just plugging everything to the formula. So we plug in B1, there's a T quantile, and SLF, and the square root of sigma xi minus x bar squared. The final answer is this. It is from 0.000448 to 0.0000526. And to interpret the slope parameter, the confidence interval for the slope parameter. This is like a template. So we are 95% confident that for every unit increases in PSI, so this is X, for every unit increase in X variable in PSI in the context, the density, this is the Y, the density of the next ceramic increase by anywhere between these two numbers. Okay, we are 95% confident that with one increase in the X response variable, the increase caused by the X and Y would be anywhere between the two ends of the confidence interval. And you can do all of this in JUMP. So these steps shows you how to do this, how to fit it into the inference in JUMP. It's the same steps as we did for chapter 4, and there is also going to be another video showing you how to get the output. And this is the output of this ceramic data using JUMP. We got a plot with a scatter plot with a fitted line on top of that, and we have also got the formula for the fitted line, and we have the summary of fit. We have R square. This shows the goodness of fit, and the root mean square error. This is just SLF. Mean of response is just Y bar, and number of observations is just N. And we also got the analysis of variance table. This is something we will be doing later. And we also have the parameter estimates. Okay. So for the inference, we will look at the parameter estimates table. We have seen that how to do that by hand, and it's more convenient to get the same confidence interval using JUMP. Because what JUMP have is that you have already got the B1, you don't need to calculate it yourself. This number is also from the table. And this sample standard deviation of B1 or standard error of B1 is 1.817 times 10 to the minus 6. This is from here on the second row of the parameter estimate. So in the parameter estimate, the second row pressure, this row corresponds to the slope parameter, and the estimate B1, and this is the standard error of B1. Okay. And then the confidence interval is just B1 plus or minus T times standard error of B1. Okay, B1 is this number, and T is 2.16, and standard error B1 is this number. And what you need to do is just to use these two numbers provided by JUMP to get this 95% confidence interval. So if you do it by hand, you need to calculate this sum of square residues and also the SLF. But if you use the parameter estimates table in the jump out, you don't need to do that. And we can also do the hypothesis testing to test if the slope is equal to 0. We will do a two-sided hypothesis test. So the alternative is beta 1 is not equal to 0. And we do the hypothesis test at a significance level alpha equals 0.05. And here are the steps of the hypothesis testing. First, the null and alternate hypothesis, beta 1 is equal to 0, or beta 1 is not equal to 0. The significance level alpha is set to be 0.05, and the test statistic used is this. So the number here is 0, so we have b1 minus 0, and in the denominator we have the standard deviation of b1. Or the samples, we have the standard error of b1, sorry, or the sample standard deviation of b1. And if we assume that no hypothesis is true, and the model assumption holds, which means that the yi's are equal to b naught plus b1 xi plus an error returns epsilon I, where epsilon i's are ID normal 0 sigma squared. And under these assumptions, we have that the test statistic will be following a t distribution with degrees freedom n minus 2, 13. Then we plug in the data to the form of the test statistic. We will get the observed test statistic. It is 26.8. And in the jump output, this thing is called T ratio. And we can calculate the p-value like this. The p-value is the probability that you get a more extreme observed test statistic. So because it's a two-sided test, so it is the probability of the absolute value of the t random variable is greater than the absolute value of the observed test statistic. The t13 here is just the t random variable with the t distribution with 13 degrees freedom. Calculating this probably gives you a p-value that is very small. It is less than 0.001. And in the jump output, this number is also in the parameter estimates table. It's called a prop greater than absolute value of t. So with this small p-value, the p-value is less than the significance level alpha, we can reject H0 and conclude the alternative. And the conclusion in layman's term would be there is overwhelming evidence that the true slope of the line is different from 0. Okay. let me show you what are the t ratios and greater than absolute value of t in the table. So this is the t ratio. And this is the p-value. You need to be careful that this t ratio is just, this is just a b1 divided by the standard error of b1. So you can use this when you do a hypothesis testing. You can only use this. You can only use this value when you do hypothesis testing of beta 1 is equal to 0 or not. Because if you are doing a hypothesis testing for something like this, then the test statistic should be this. Then you cannot use the t ratio here, because what t ratio gives you is just this. And when you do the hypothesis testing of you want to test whether the slope is equal to 0 or not, the test statistic is just this, so you can use the t ratio and you don't need to calculate the test statistic yourself. And the p-value is also ready to use, because the probability greater than absolute value t is just based on this t ratio. So you can use these two values only when you are doing a hypothesis testing like this. Okay, you can only use these two numbers when you are testing whether the slope is 0 or not. Okay, that is the t-test for testing this, the hypothesis for testing whether the slope is 0 or not. And there is another method for testing the slope is 0 or not. And the method is called the analysis of variance method, or ANOVA. So when you do a simple linear regression, you can always decompose the total sum of squares to two parts. So this is the total sum of squares. It is the sum of yi minus y bar squared. It can be decomposed into, this is the sum of squared residues. We call it the error sum of squares. And this is the sum of, there is a square here. So this is the sum of y hat minus y bar squared. And we call it the regression sum of squares. And if you remember what we did in the variance explained by the model using R squared, you should know that this is just the total variance in response. And this SSR is just the variance explained by the model. Okay. And here is the fact. Under the assumptions of SLR model, and when you're assuming that the null hypothesis is true, then the test statistic F, which is SSR divided by 1, divided by SSE divided by n minus 2. This test statistic would have an F1 n minus 2 distribution. So for F distribution, there are 2 degrees of freedom. So this test statistic would have a F distribution with degrees freedom 1 and n minus 2. So you can review the F distribution in the chapter 5, part 5 slides. With this test statistic, what we will do is that we will reject H0 in favor of HA when the F is large. Okay. So the p-value would be the probability of the F random variable. This is F1 and minus 1 random variable greater than the observed F. And there is a relationship between the t statistic and the F statistic. In fact, the square of the t statistic for testing this hypothesis, this is what we used. There is a square missing. This is what we used for testing the slope is 0 or not. And if you square this test statistic, you get this. And this is exactly the F statistic. So the square of the t test statistic would just be the F statistic we used in the ANOVA method. So it has an F1 and minus 1 distribution if H0 is true. And this large T would favor HA. So if the H0 is false, that means your absolute value of T will be large. So the square of T would be large. And that's why we say that if you got a large F, it can be used as evidence against H0 in favor of HA. Okay, so these two are actually equivalent. F large is equivalent to the T large. That is the value of T large because F is just the square of T. And from here, you can also find that the p-values you got from these two different tests should be the same. right? Because for the t-test, the p-value is the absolute value of the t statistic is greater than the observed test statistic. This is the p-value, and this is equal to t squared is greater than t squared, okay? And the t squared is just the f statistic, and the observed t squared is just observed f statistic. So these two tests should give you the same p-value. And the calculations of the ANOVA method can be summarized in something called an ANOVA table, like this. There are 5 columns. The first column indicates the source of the variation. There is a total variability and also variability from error and the variability in the model. And in our model, we are doing a regression. So we can also use a regression as a source. And the sum of squares, the corresponding sum of squares are SSR, SSC, and SS total. Degrees freedom are for the regression is 1, and for the error terms is m minus 2, and the total degrees freedom is m minus 1. The ms is the mean of sum of squared, is the mean of squares, and the mean of squares, the regression mean of squares is just SSR divided by 1. So it is the ms is just SS divided by df. Okay, so for MSR, it is SSR divided by 1, and MSC is SSC divided by m minus 2. And F would be just the ratio of MSR and MSC. And this analysis of variance table is also contained in the jump output. So you got as a source column. So in the jump, it is not using regression, it is using the model for the source. But it is just the same thing, because the model is just a regression model here. And we've also got the sum of squares and the mean squares, and also the F ratio. So the F ratio is just the F. And there's one more thing for the jump output. We've also got the p-value for it. This is just the p, the probability of f, the test statistic is greater than the observed test statistic. And in the ceramic example, this is the output of the ceramic data. We find the p-value in F test is very small. So again, we can, because the p-value is small, we can reject H0. And the conclusion would be that there is a significant evidence that the true slope is different from 0. Because remember, our hypotheses are this, and the alternative is that the slope is not equal to 0. We reject the null, and there is evidence that the slope is different from 0. Okay, that's all for the inference for simple regression. Today is only for the inference for the slope parameter, and we'll have more inference of simple linear regression in the next video.